Yes, so Leximancer does implement a style of content analysis. I guess it's different from some of the forms of content analysis you might have seen, in that the concepts it discovers by itself are fairly simple concepts, but there are lots of them. So the philosophy there is, it's called complex systems theory, but if you have a lot of simple things but look at their interactions, you can find complex ideas. So that surprises Leximancer users sometimes. When they first use it, they wonder why are all these simple concepts. So what you need to do is you look at the connections between them. So the reason the Leximancer concept map looks like it does is that it's showing you the clusters and the connections between a set of simple concepts to show you some complex ideas. Mm-hmm. And it's a way that a computer can measure complex ideas from data without being particularly smart, right? Because computers aren't particularly smart. But using this complex systems, it's actually called a semantic network, a complex semantic network that it builds. So when you see a concept map Leximancer produces, that's what's behind it. And what you need to do is look at the linkages between those ideas and the pathways. That's a concept map extracted automatically from a report. And, it looks a little complicated, and that's because it's a complex network. But you can simplify it by just looking at the clusters. So I can see the major themes here, and these are fairly complex ideas. If you look underneath them, there are stories here of pressure testing pipes and pipework, underground installations, gas tanks. We'll look at a little bit further. There's responsibility for installation over here. And parts of the factory structures here, the building and the ground and so forth. And I can see there's safety and risk and time over here. And, the more you reveal these concepts using this slider, the more you see, you're drilling down. It's like starting looking at a satellite view of a continent and then coming lower and lower until you see, more and more details emerge. So this is, as I said, how a computer can capture a complex information space. The hot colors are the most connected. So you see the red cluster here, the red theme. These concepts have the most connections to each other and are most supported in the text. So what that means is, if every concept, like here's the concept of customer, I've clicked on it and you can see in the semantic network, it has relationships to all the other concepts, or most of them in this case. And you can see that customer has a strong connection to responsibility and supplier and supply. And there are lots of text locations that support that. So this says that the concept of customer is coded into 79 text segments along with the concept responsibility. And so all in all, if I add up all these co-occurrence counts, it gives me the connectivity score of this theme, and it's got the highest support in the discourse. So if you added up the co-occurrence counts of all the concept codes in this theme, you get a number, and that gives you the connectivity score. And if you rank them, then you get something like this. So the first tab, called the analyst synopsis, actually tries to show you this at the thematic level. So I can see the red theme, pipework, has the highest connectivity score. It has 8,000 hits in the pieces of text which support it. And I can see the concepts that are contained within that cluster. So if you look within here, you can see the cluster contains quite a few stories. This lists those concepts, and you can see some of those, the top 5 pieces of text which support this theme, just for a quick view. But if you want to drill down and see all the texts that support this theme of pipework and LPG tanks and so forth, you click on this list of concepts, and it will show you all those 8,000 text segments that support the theme. And you can read these as a qualitative analyst might do. You would read these until you stop being surprised. You stop seeing new ideas being mentioned, and you can use these in your as quotes in your report. And so this is part of the sense-making approach. You're looking at the map, however you present it, hiding the concepts, starting at a very high level, bringing in the concepts, drilling in. These are all fine, and they give you a framework to say that, well, time as a major theme is important, but what's it composed of? Well, mostly it's about health, safety, and inspections of premises, in actual fact. And so you can and you should then go, let's say, to the annual synopsis and look at time here. You see what it's composed of, and then drill down to have a look at all those texts to understand what they're saying. So this is, even though Leximancer puts it on a more quantitative footing, this process, as content analysis does, it's still important to understand what these artifacts mean. What does a connection between risk and company? So what does that connection, that relationship between risk and company mean? So I've selected risk by clicking on it, and I can see what it co-occurs with, and I can go and find any concept that I want to understand its relationship with. So risk, company, co-occur in 36 text segments. If I click on that number, I can go and understand what they mean by risk to the company. What is that sense? So it looks like they're talking about risk assessments. The company requesting risk assessments. And I guess there's a sense of liability which develops because this is a major industrial accident, which this inquiry was looking into. So, you don't have to guess, and you don't have to just rely on the concept map, but it does give you a framework to see the information space and what questions you should ask. So if you think of it that way, this sort of model tells you what questions you should ask, what relationships are important to the authors of this material, and what are not important. So if there's no evidence here of an idea you thought should be here, or two concepts which you thought would be strongly related are on opposite sides of the map, then that's telling you that's not important in the data. The default in Leximancer is very exploratory. You put in the data, and a couple of minutes later you get a model, and it develops the concepts from the data. From this data set, which is a bunch of transcripts, quite a lot of data actually, because about 20 days of transcripts. It's developed these concepts as being important to this data, not to someone else's data or some what they call supervised training done by someone else. This is done on this data. So these are important ideas given the word co-occurrence usage. And these are concept names. So what it develops is, if I look at a concept like corrosion, you can see in the thesaurus tab, which is where I am, you can see the words that co-occur, that travel together as a family around the idea of corrosion. So you can see pitting and protective and cell, ungalvanized, aggressive corrosion, penetrated. So yeah, you can kind of guess by now that this is corrosion, talked about in the context of, well, we don't have to guess. That's the wonderful thing. If we find corrosion here, if you can't find a concept, use the pull down at the top here. This is sorted alphabetically, and you can click on corrosion, shows you where it is, shows you what it's related to. So corrosion protection, steel, underground pipes. It's a pretty good synopsis of what it is, and I can see on the map, it's carried forward here. You can see what these grey lines show, that the narrative is about corrosion protection of pipes, and pressure testing. So I guess it's a machine which is made to extract the concepts from your data, develop the vocabulary code books for every concept, to code those back into the data so it can measure how many times these concepts co-occur in the text, to develop what's called a concept co-occurrence network. Concept A co-occurs with concept B 300 times, which has a certain strength. And then from those links, it develops this map to give you a visual artifact. But from there, you are on your own. So you can quickly get to this point, but then you need to sense make. You need to work out what each of these themes mean, what some of these important pathways, the narratives, what they're actually meaning in detail. And so that's where you take over. And at that point, you can switch from exploratory mode to what you might call confirmatory mode, or theoretically driven, top down, where you say, well, okay, I found that they talk about, in this case, well, up here, this theme, this area of the map, it's talking about letters, pages, documents, reading statements, looking at, indeed, evidence. And this is because it's an inquiry, so this is legal procedure. Now, it's important to these people, but it might not be important to you. So you can remove these concepts from the map, and there's a place where you can do that, so that you don't see that in the model. You can add your own concepts. So if you find there's a concept that's not here, more abstract idea, or maybe a less frequent idea which didn't emerge in the automatic, you can add that as a concept. So you can see how they were placed in the terrain, whether they were near the legal procedure, the new concept you're interested in, or whether it was all about the engineering infrastructure. And you can take a lot of control. You can, in fact, use a technique called profiling to say, this is all very well, but I want a map which has concepts all about health and safety. So it wouldn't look much like this, but what I could take from this is that, well, the most important concept, I can see there is safety and there's risk. So, but I don't care about the rest. I want a map which has 60 concepts which are all about different aspects of safety and risk. And you can do that in Leximancer using the profiling technique. You just choose these two and say, show me a concept map which is focused just on that idea of safety and risk assessment. So you can make it a lens to look at the data any way you want. But that's moving forward to do more theoretically driven or research question driven analyses. Anyway, that's probably enough about that. I was talking to the people from CSIRO the other day, and we looked at it in a very social network analysis view. A lot of young researchers haven't come across social network analysis, but it was popular in the early 2000s, and it's still hard to beat as a method to look at these sorts of networks. Textual information spaces lend themselves more naturally to a network analysis than any other, I think, because, well, there are several reasons, but it's the nature of language that we use words a certain way. We use, like, if you look at the rank concept list, which is just the frequencies of these codes, you can see there are a few very frequent concepts right at the heart of the matter about pipework and tank and paragraphs and risk. And then down the bottom, there's a whole lot of much less frequent concepts. This is it's a distribution and a pattern of information which we see in natural systems, and it's called a small world network. There was some research about that in the late 90s, early noughties, about characterizing these sorts of network. And we find them in the internet, computer networks, human language, natural language. It obeys this distribution. Many sorts of relationships between people and organizations, they obey this sort of rule. So they are naturally networks with a type of hierarchy. So, and this is what you can see using this slider. You can see there are these key hub networks which dominate the regions. So people are talking about LPG pipework, and so these are very big nodes in the network. They have lots of connections, and so they have big gray dots. And there are other central nodes like risk and time, and we can look at those. Then, as we reveal, you see a whole lot more come in at the lower stories. Maybe it's like a mountain range. You can see the peaks, and you can see a lot of detail underneath. That's a very natural network, and because language forms these sorts of networks, Leximancer is a model which uses these sorts of complex hierarchical networks to capture that information. So, I do get, there are researchers who scratch their heads and do ask, well, it's a very complex model. Why do you use it? It's simply because it is the natural form of information that comes out of natural language. So I guess, we've looked over the years at other ways you could model it, but this is the natural way to capture the information. So I guess we stick to it because we haven't found a better one. All right, anyway, so there's just a quick introduction to the theoretical frameworks behind Leximancer and the driving motivation, which is, we know there's a thing called Zipf's law, ZIPF, and we've known that for, I don't know how long, 50 years more, probably more, that natural language forms these sorts of small world network statistics. And yet people still resist using complex semantic networks to model textual information. I'm not sure why, because there is no better way, in my opinion.
I get a bit concerned about using like other programs, I guess, like NVivo. Like I haven't used it properly yet, but in terms of like bringing my own biases into that kind of content analysis.
Yes.
This like Leximancer seems to avoid that in my, like from how you're explaining this, it seems.
It certainly gets you started in a very data-driven way. So this is an exploratory map taken straight from the data and grounded completely in the data. And yes, there are a few simple algorithms Leximancer uses to select the important concepts, and there's a machine learning algorithm to develop the vocab lists around each. But once you've got that, the fact that tank co-occurs with valve, which causes them to come together quite closely on the semantic model, because of the valve and the tank and the steel and the gas, they're obviously semantically very close, and the model brings them together and shows that. But you don't have to guess. You don't have to defend some algorithm Leximancer to say, why is this valid? Why is this construct valid? Or if you need to, or you can just say tank and valve are coded together in 189 text segments. I can show you all of those. Obviously, it's an important construct. There probably isn't a more important one here. So the data supports the model in a very transparent way. So if anyone, a reviewer of your article or someone in the seminar asks, well, how do you know there's a relationship between tank and pipe, or building and whatever it is, the tank, or I see explosion and LPG, you can always show them the text which supports that relationship. So, it is a valid model. Now, the other question, so yes, it's a valid model, and you can point to the text that supports every relationship in this network, every link in the network, and every concept is supported in the data. So it's a valid model. But the question that you can be asked, and a much more sensible question, is it the only valid model? And that's a far more interesting question. And you have to say no, because as you know, having used NVivo, there's many, many ways you can code text, right? It depends. If you choose a theoretical approach to coding text, you take your theory and it drives the concepts that you want to code. So for as many theory or theoretical frameworks as you could come up with, there's that many ways to code text. If you talk to someone in English literature, they have different frameworks for analyzing literature. Marxist, feminist. These days, I'm sure there are environmental frameworks for examining literature. And all those are different ways to code the text. If you look at library science or information science, which I was studying when I developed Leximancer, there are different ways you can classify and code any document. You can use data-driven methods, which is what Leximancer by default does. So this says, okay, there's enough text which talks about disaster and safety and site visits that I'm going to create a concept around those, because if enough people are talking about it and they're using a rich language to talk about it. So it is data-driven by default. But that won't necessarily be what you do if you had a theory, because you might not care about legal procedure, or conversely, that might be all you care about. So there's a million ways you can code a document. But you could demonstrate that this is a valid one by showing the texts that support every concept and every connection between the concepts. So, okay, don't want to get too theoretical, but we do have, a couple of advanced users on the call. So I guess I'm just sharing some of my some of the philosophies that I was exposed to when I was developing Leximancer, ideas from complex systems, from social network analysis, and also epistemology and ontology, things from information science, how people view an idea. See, what the secret that I don't mention too often about Leximancer, because I guess it makes some people raise their eyebrows, is that what he's actually trying to do is trying to look inside the minds of the people who wrote the content and develop a mental model of how they were thinking about the topic that they were writing about. Now, obviously, we can't reach inside their minds and find that neural network, that mental model in their brain. But from the usage of words, the challenge was to try to come up with a model which captures that captures the semantic network of words that they used to describe the situation. And if you look at our validation paper, which I published with a cognitive psychologist, Mike Humphreys, in 2006, that's exactly what we were trying to validate. We were trying to show that the different documents created in different time periods, maybe hundreds of years apart, by different people, but based around the same idea, the same conceptualization of a situation, that the models that Leximancer extracts look similar. And so that's why we got a Bible in translation in French, a Bible translation in English, or the rules of baseball and the rules of cricket. I mean, those two games have both come from the same original game, but 400 years ago. So, but their maps are extremely similar. And it's not magic. It's not a mystery once you look at it, because the roles of the pitcher and the bowler and the batter and the batsman, they are very similar. And what they do is very similar. So the semantics are similar. So the model comes out really quite similarly, the semantic map that you get in Leximancer. So this is the challenge that I was working on, and it's a fairly good solution. Keep working on it and trying to find new ways to improve it. But it's pretty good at what it does. So probably a good time for questions now from anyone.
Yeah, in the slide that you are sharing with us, I see relevance against the counts, but in my version, I see likelihood.
Yes.
How are they two different?
So let's pick a concept and have a look. Explosion. So I'm getting likelihoods here, but you kind of need to look at what goes on in the second tab. Mm-hmm. Because what I've selected a concept, explosion. Now this tab changes its function, its mode. This shows me the concepts that are related to explosion, ranked by likelihood. So the most likely concept to co-occur with explosion is fire. So it's likely. But if I go back to the ranked view, so if I press on this ranked view button, this takes me back just to the master frequency list.
Oh, okay.
And here, you're not looking from the perspective of any particular concept. You're looking just at the whole list. Mm. So this is like just the frequency ranking of concept codes. So what's the most frequent concept in this whole document set? It's pipework with 1,715 counts. And then these are relative to that. So that's the most frequent concept gets 100%, and then tank is 81% of that. So this list, the way you come into it by default, shows you the master list of frequency rankings. But if I select a particular concept in any way, like either clicking on it on the map or clicking on the name of it here. So if I click on the name of underground, if I click on underground here, or in the same way, if I click on it on the map, you're now looking at it from the perspective of the concept of underground. And you can see that because it says here, selected concept at the top. Mm. Now we're looking at co-occurrence counts. Underground co-occurs with corrosion, pipework, protection, service. And I can start to get a sense of, well, okay, they're talking about underground pipes and their protection by the look of it. Looking at the co-occurrences, you might call these relationships. These are semantic relationships in the network. So this is when it flips over to showing likelihood.
Is count the counts of those concepts in the blocks of text?
Yes.
So is it similar to the hits?
Yes.
Which is used for the concept? No, I mean the themes. But here the counts is used for the concepts, right? But otherwise it's same.
Yes, it is. They are the text segments where in this case, Leximancer is content analytic behind the scenes. So every text segment that you upload into a project has been coded with some concepts, often multiple concepts. So this is showing me that there are 139 text segments which have been coded with the underground code and the pipes code. Okay?
Yeah.
So if I click on 139, it shows me those. So it actually does a search for which text segments are coded with underground and with pipes. And you can see it up here in the search box. And these are basically the hits. And here you can see there's 139 of them. And these have been coded with underground and pipes. So if we have a look at there's the word pipes is there. But you'll see that the word underground is not in this text segment. That's because, remember, these are concepts. These are the concept of underground has many words which indicate that they're talking about something that's under the ground. So there's words like deterioration, weather. There's enough words here which are indicating they're talking about underground pipes and deterioration. So you get that sort of implicit coding. So that's why the thesaurus does what it does.
It's Russ.
If I go down and have a look at underground as a concept, can you see that these are the words that, these are the vocabulary that goes along with underground, and this is used to predict. So if it finds a piece of text that talks about conduits, spotted, lagging of pipes, in other words, mounded, in other words, earth, if it finds a few of these words in a piece of text, it says, well, this is talking about something that's underground, because it's using some of the vocabulary. So it will code it with underground, even though it doesn't mention that word. This is why we do use the word concept. A lot of people in text analytics, they talk about concepts, but what they're actually talking about is words, keywords, but we don't. We mean it. Well, we try to get closer to the idea that this is the concept of underground, but it's defined and represented by a list of different words, which the people who wrote this material, it was in their minds that if it's underground, well, there's probably lagging involved. There's probably terminating pipe work. There's spotted with corrosion. So this is more like an idea than a keyword.